So we all know the Euler-Lagrange equation. The Euler-Lagrange equation applies when we're trying to minimize some integral of the function f, and we just use the one variable version y dot, and x. This equation, the Euler-Lagrange equation, tends to give you a second order differential equation, which is somewhat challenging to solve in some cases. It's a lot easier if this f does not depend on x. If that f does not depend on x, then there's a shortcut, and I can best explain the shortcut by working backwards. Let's try and calculate how this thing here, how that behaves. Now if we can expand this out, we use the product rule, and then we get the derivative of this, remembering that this is a function of y dot, and x, so we're going to get three terms. We're going to get the dependence where y dot depends on x, we're going to get the term where y depends on x, and we're going to get the very explicit dependence of f with respect to x. Now in the situation where this term here is 0, i.e. f does not depend on x, then we can make a simplification. We can make an immediate simplification, of course, because this term here cancels with that term there because they are equal and opposite. And the final two terms we can look at a little bit more carefully because this one here, this bit here, that's very familiar. d dx is exactly that bit there. So of course this bit here is just equal to this. So we're going to get a y dot delta f delta y minus exactly the same thing. So those two also cancel. So in other words, using the Euler-Lagrange equation and the fact that df does not explicitly depend on x means we get that this thing here is constant. And the nice thing about this is that this is a first order differential equation typically. And that has a name. It comes up so often that it has a name. It's called the Beltrami identity, and we're going to use it many times. In fact, I just proved it for the single variable version. If we have the multiple variable version, then everything is very, very similar, of course. What we have is an Euler-Lagrange equation for each variable. So we're going to have a set of Euler-Lagrange equations. This is going to be a vector. This is now going to be a dot product. Here we're going to have a whole sum of terms. And so down below we'd have the sum over j of all of these terms, and each of those are individually 0, so that still sums up to 0. And so that dot producted term in the brackets is constant, and so we have the multi-variable version of the Beltrami identity. Now the advantage again of the Beltrami identity is that it's a first order differential equation instead of a second order differential equation, which is what we get from the Lagrange equations. If we have a function of more than one variable that doesn't depend on the integration variable, and therefore we can use the multivariable version of the Beltrami identity, then the Beltrami identity, you'll note, only gives us one equation. And so we have one first order differential equation from the multivariable version of the Beltrami identity, which means we can't actually solve all of the dynamics from it because we need two differential equations for our two variables. But it still holds true for autonomous systems, and it can be used to get constraints for the system. It can also be used to solve for the full dynamics, provided you use it with an appropriate subset of the Euler-Lagrange equations.